Let's imagine a situation where a group of people each has to make a simple binary choice. They could be deciding yes or no on some question, or choosing between two political candidates. To put this into mathematical terms, we'll call yes a +1 and no a -1. Now let's start simple with just two people, Alice and Bob. Suppose they both vote yes, which will represent their estate as +1. To keep things simple, we'll label Alice's decision as S1 and Bob's as S2. What happens if we multiply their choices together? If Alice and Bob both choose +1, their product is +1, and we can think of this as a state of agreement. If Alice chooses +1 and Bob chooses -1, their product is -1. This is a state of disagreement. The same is true if the roles were reversed. And if they both choose -1, the product is once again +1. They still agree, but this time on saying no. So the product S1 times S2 gives us an elegant way to tell whether they agree or not. But in the real world, people aren't isolated. Their decisions are often influenced by their relationship with others. You might say there's a tension between them. Let's represent this tension with a value, which we'll call J12. That lives on the connection between Alice and Bob. We can think of J12 as a dial that sets the tone of their relationship. If J is positive, we can say the relationship is tense, maybe even competitive, and they are rivals. If J is negative, their relationship is cozy or friendly, and they are cooperative. And if J is 0, they have no influence on each other at all. So, you might ask me, how do you combine all these ideas? We've got Alice's choice, Bob's choice, and the tension in their relationship. But what's the connection between these things? We can define a single number that captures the state of the whole system. Let's call it the conflict, or for those with a physics background like me, the Hamiltonian, denoted by a capital H. The conflict is simply the product of Alice's choice, the tension J, and Bob's choice. Simple as that. Now let me show you what this means in practice. Suppose Alice and Bob have a cozy relationship, so J is -1. If they both agree and choose +1, the total conflict H is -1. That's a low conflict state. But if Bob disagrees, the conflict becomes +1. This makes sense. In a cozy relationship, disagreement leads to higher conflict. Now, what happens if we dial up the tension so their relationship is tense, with J equal to +1? In this case, their disagreement actually leads to a low conflict, -1. But if they agree while in a tense relationship, the conflict becomes high and jumps to +1. In this state, they're almost expected to disagree. This leads to a fascinating question. The tension J is fixed. What choices will Alice and Bob naturally make to minimize the total conflict? The lowest conflict, or lowest energy state, has a special name in physics. It's called the ground state. Let's try to find it. In the cozy case where J is -1, we can calculate the conflict for all four possible combinations. The lowest value, -1, occurs whenever they agree. This means +1 +1 is a ground state, but so is -1 -1. That means this system has two ground states. Now, what if the relationship is tense with J equal to +1? Again, the minimum conflict value is -1, but this time it occurs when they disagree. So the ground states are +1 -1 and -1 +1. You might wonder what happens with three people. So, let me introduce a third person here, Charlie. Now, instead of just one relationship, we have three between Alice and Bob, Alice and Charlie, and Bob and Charlie. Each of these connections gets its own tension value, J12, J13, and J23. The total conflict of the system is simply the sum of the conflicts from each individual pair. It's a conflict between Alice and Bob, plus the conflict between Alice and Charlie, plus the conflict between Bob and Charlie. And this pattern continues. If we add a fourth person, Diana, we now have 6 connections in total. The total conflict is just the sum of the conflicts across all of these 6 pairs. As you can imagine, writing out every single term gets long very quickly, but mathematicians have a beautiful shortcut for this kind of sum. We can say the Hamiltonian age is the sum over all pairs of people I and j of Si times Jij times Sj. This formula has 2 key components, the state of the spins Si, which for each person is either +1 or -1, and the tensions Jij, which we can think of as the elements of an n by n matrix describing the entire network of relationships. Now just a quick side note here. It's fair to assume that in the real world, the tension is mutual. The way Alice feels about Bob is the same as how Bob feels about Alice. In other words, Jij is equal to Jji. This means the tension matrix is symmetric. So this symmetry allows us to rewrite the sum in a more general and often more useful way. Instead of summing over only the unique pairs where I is less than j, we can sum over all I and all j, as long as we multiply the whole thing by 1/2 to avoid double counting each relationship. And for those of you familiar with linear algebra, you might recognize this structure. This entire expression is simply 1/2 times the vector of S spins S transposed times the matrix of tensions J times the vector S. This is what that compact formula actually represents, a neat, clean way to capture all the pairwise interactions in the entire system. The astute among you may ask me, but how do you find the ground state of a system like this? Well, the most direct brute force approach would be to check the conflict value for every single possible configuration of spins. But just how many configurations are there? Well, the first person has 2 choices. For each of those choices, the second person has 2 choices, and so on for all n people in the system. The total number of configurations is 2 multiplied by itself n times, or simply 2 to the power of n. But what does that number actually look like as n grows? At first, for a small number of people, it seems manageable. When n equals 5, there are 32 configurations to check. But as n increases, this curve bends upwards with terrifying speed. This is the nature of exponential growth. By the time we get to n equals 30, the number of possibilities has exploded to over 1 billion, and the problem gets unimaginably big, incredibly fast. To put this in perspective, for a system of just 300 people, the number of possible configurations, 2 to the power of 300, is a number so vast that it's greater than the estimated number of atoms in the entire known universe. So simply checking every possibility is not just a slow. For any reasonably sized problem, it's physically impossible. This is what makes finding the ground state of these systems such a profoundly difficult and deeply interesting problem in physics, computer science, and mathematics. But you might be wondering, so what? Is this just a niche problem for physicists studying magnets? Or is there something deeper going on here? It turns out this Ising problem is actually a universal puzzle, one that secretly describes a huge number of other difficult problems that seem completely unrelated at first glance. To see how, let's take a look at one of those other problems. It's a simple puzzle that you could try to solve yourself, the number partitioning problem. The rules are simple. Given a set of numbers, can you divide them into 2 groups that have the same total sum? For a small set like 8, 7, 6, 5, you might be able to find a solution with a bit of trial and error. Let's try to reframe the problem. Instead of thinking about putting numbers into bins, let's think about assigning a spin to each number. And let's say that if a number goes into the first group, we'll assign it a spin of +1. And if it goes into the second group, we'll assign it a spin of -1. You might see where this is going. Take each number, multiply it by its assigned spin, and add them all up. If we do the math, we get 8 minus 7 minus 6 plus 5, which equals 0. That isn't a coincidence. Think about what this sum actually represents. It's the sum of the first group minus the sum of the second group. So, saying that the two groups have an equal sum is exactly the same as saying this special spin-weighted sum is 0. Our goal has been transformed. Can we find a set of spins Si that makes the total sum of Si Ai equal to 0? But hold on, you should be a little skeptical here. Our original Ising Hamiltonian had pairs of spins Si times Sj, and those J tension values. This new formula only has single spins. How can this possibly be the same problem? Well, here's the final piece of the puzzle. Consider what happens if we take the entire sum and square it. If our goal is to make a number equal to 0, that's the same as trying to make its square as small as possible, right? Now, if we expand this squared term, and you can pause and try this yourself if you'd like, something amazing happens. This expression splits into two distinct parts. The first part is just the sum of the squares of all our original numbers. But think about that for a moment. Those original numbers are fixed. They're given to us. So this part of the expression is simply a constant value. It doesn't depend on our choice of spins at all. Now look closely at the second part. What remains is a sum over all pairs of spins I and j of Si times Sj, multiplied by some other values. This structure should look very familiar. It's exactly the form of our Ising Hamiltonian. If we simply define the tension Jij between any two spins to be the product of their corresponding numbers, Ai times Aj, then minimizing this expression becomes mathematically identical to finding the ground state of that specific Ising system. And this isn't just a neat trick. The Ising model is like a master key. Many of the most notoriously difficult problems in computer science and operations research can be translated or mapped into the language of finding an Ising ground state. Problems like maxcut, which involves dividing a network into two parts, the famous traveling salesman problem, even problems from entirely different fields, like the k-satisfiability problem from logic. All of these problems, despite appearing so different on the surface, share the same computational skeleton. They're all, in essence, about finding the one configuration out of an astronomical number of possibilities that minimizes some global conflict or energy. And this is why scientists, engineers, and mathematicians are so deeply invested in this problem. If you can build a machine or an algorithm that reliably finds the ground state of an Ising model, you haven't just solved one niche puzzle. You've created a powerful tool for tackling thousands of others. So, this brings us back to our central question. If checking every state is impossible, how can we ever hope to find this ground state? The short and perhaps surprising answer is, for a general complex system, you don't. At least not in an exact way. There is no known algorithm that can efficiently find the exact ground state for any arbitrary set of tensions Jij. However, for a few very special cases where the network of connections is highly structured, mathematicians and physicists have discovered clever ways to solve it exactly. The most famous example is the 2D planar graph, which is a graph that can be drawn flat on a plane without its edges crossing. In a landmark 1944 paper, Lars Onsager unveiled a stunning analytical solution for these systems. But that level of precision only works because of the strict two-dimensional structure of the grid. The moment we move into 3D or allow more complex connectivity, an exact solution once again slips out of reach. Things get even stranger when we move to spin glasses, where the tension between spins are completely random. Finding the ground state of any specific spin glass remains incredibly difficult. However, thanks to the monumental work of physicists like Giorgio Parisi, we now have a profound mathematical understanding of their statistical nature. Parisi's Nobel-winning contributions revealed the incredibly complex structure of the low-energy states. While this doesn't provide a straightforward method for locating the ground state of a given instance, it offers profound insights into the nature of complexity itself. What about the messy, complex real-world problems we saw earlier? For those, we need a different approach. If you can't compute the answers directly, perhaps you could build a physical system that naturally finds the answer for you. This is precisely the idea behind machines like this one, a quantum annealer. It's not a general-purpose computer, but a highly specialized piece of hardware designed to do just one thing: find the lowest energy state of a physical system that is programmed to behave just like our Ising model. It tackles the problem not by crunching numbers, but by using the laws of quantum mechanics to feel out the entire landscape of possibilities at once and settle into the valley of lowest energy, the ground state. So, how do you make progress on a problem that seems fundamentally unsolvable? Sometimes the answer is to step back and change the question entirely. As said before, the Ising model is defined by its matrix of tensions, the Jij values. For decades, researchers focused on cases where these tensions were either uniform and regular or completely random. But then, a young physics student began to wonder about the nature of this J matrix itself. He imagined a system where the components weren't all identical, but had distinct ranks or identities, a hierarchy. And he posed a simple, imaginative question. What if the interaction between any two spins was a direct function of their rank? He began with the simplest rule he could think of. The tension between any two spins is just the sum of their ranks, Jij equals I plus j. With a small computer, he began to explore. He set the number of spins to 10 and had the machine search through all 1024 possible configurations to find the one with the lowest energy. The result was surprisingly simple. A clean split. 2 blocks of spins, all aligned together. Curious, he tried it again for 11 spins. The same pattern emerged. For 12, 13, 14, and 15 spins, the same beautiful, simple structure appeared from the complexity every single time. This was the moment of discovery, the sense that this wasn't a coincidence, but a fundamental property of the world he had created. He pushed the idea further, discovering that this was just one instance in a broader family of rules, each governed by a single parameter, d. For every value of d, whether positive or negative, the same elegant two-cluster pattern consistently emerged. While the size of the cluster varied, the fundamental structure remained unchanged. He had uncovered a vast new class of systems, each complex and fully connected, yet all exhibiting the same simple, predictable ground state pattern. But as he stared at these patterns, he noticed something even stranger. It wasn't just that the ground state always formed 2 clusters. When he examined the size of the first cluster, and let's call it M, and compared it to the total number of spins n, a new pattern emerged. He saw that for a given rule, say d equals 1, this ratio, q, which is m over n, appeared to stabilize, converging toward a specific constant value as n grew larger. He could track this convergence with complete certainty up to around n equals 30, using brute force to ensure he had found the true ground state. But beyond that, the calculation became impossible. He hit the 2 to the power of n complexity wall. He was stuck. And here, he took a crucial leap of faith. He made a bold assumption. What if, he thought, the 2-cluster pattern wasn't just a coincidence for a small n, What if it was a fundamental law of this system, true for any n? This assumption changes everything. The problem was no longer about searching through an ocean of 2 to the power of n possible states. It became a simple search over just n possible cluster splits. With this new approach, he could see the convergence clearly, and he could test other rules. For d equals -1/2, the ratio q converged to a different value. For d equals 4, yet another. Each rule, each d, had its own unique constant ratio that the system was trying to reach. The pattern was real. The leap of faith had been justified. The next question was, why? What deeper principle was forcing this complex, fully connected system to always settle into such a simple two-cluster configuration? But before answering the deeper question of why, he first had to set that aside and rigorously work out the how. How could he calculate the energy of this state, assuming his postulated pattern held true, not just for small values of n with the help of a computer, but analytically with pen and paper for arbitrary n? So, having observed that the ratio q converges for any given d, the student formalized this idea, defining the interaction matrix J of n and d, and adding some terms for convenience and rigor. This new rule, Jij, equals 1 over n to the d times I to the d plus j to the d, with a final term that just means the diagonals are 0. And this defines the entire system. For example, with 5 spins and d of 2, the matrix of tensions yields these specific deterministic values. With this formal structure in place, he could now state his central claim, a postulate, that the ground state for this entire class of problems always adopts a remarkably simple two-cluster configuration, a block of +1 spins followed by a block of -1 spins. Of course, the system is free to choose any spin configuration it wants, but because of the underlying Z2 symmetry of the Hamiltonian, where flipping every single spin from S to -S leaves the total energy unchanged, there will always be at least two ground states that are mirror images of each other. In his notation, he made a simple choice. The first cluster would always be the up spins, the +1s. This naturally raises the question, how do we actually calculate the energy for this proposed state? First, we can define the outer product of a spin vector with itself, which creates a matrix where every element is the product of two spins, Si times Sj. This matrix captures all pairwise correlations between spins. Next, we introduce the Hadamard product, denoted by the circle symbol, which is just a fancy term for element-by-element multiplication between two matrices of the same size. The Hadamard product of the interaction matrix J and the SS transpose matrix is just a new matrix where each element is Jij times Si Sj. By substituting our first definition into the second, we observe that each element of the resulting matrix is exactly Jij times Si times Sj. Therefore, summing over all the elements of this Hadamard product matrix is mathematically identical to our original Hamiltonian expression. Now, let's apply this to our postulated ground state. On the left, we have the conventional form S transpose Js, and on the right, the total sum of all entries in the Hadamard product matrix. For our specific S vector of 3 +1s and 2 -1s, the SS transpose matrix has this checkerboard pattern of +1s and -1s. When we perform the element-wise product, the two matrices combine into a single matrix. To visualize this, we color each term blue where Si Sj equals +1 and red where it equals -1. And so, calculating the total H energy is now simply the task of summing up all the elements of this final matrix. The blue terms are added and the red terms are subtracted. This visual understanding leads us naturally to an analytical expression for the Hamiltonian as a function of just three variables, n, d, and a single important variable, m, the size of the first cluster. To simplify this intimidating expression for the Hamiltonian, he used a well-known mathematical tool called Fallhaber's formula, which gives a closed form expression for sums of integer powers. This formula, which involves the famous Bernoulli numbers, allows us to rewrite the giant mess of sums into a much more compact form. The Hamiltonian now depends only on n, d, and our single variable of interest, m. Since the grounded state corresponds to the configuration with the lowest energy, the problem now reduces to finding the value of m that minimizes this function. This is a huge leap. What was originally an exponential search over 2 to the power of n configurations has been reduced, thanks to the two-cluster postulate, to just checking n possible values of m. This is a polynomial time problem. We can observe this minimization process directly. For a given n and d, we can calculate the energy h for every possible cluster split from m equals 0 all the way to m equals m, and find the one that yields the minimum energy. As we increase the size of the system from n equals 10 to 15, 30, and beyond, the process remains the same. We just sweep through all possible values of m and find the minimum. But for very large systems, a more elegant method emerges. As we can see, as the value of n increases, the system begins to resemble a continuous distribution of points. The student took his next great leap. Instead of treating m as a discrete integer, he considered the limit where n is huge. In this regime, the ratio q equals m over n becomes a continuous variable, and finding the minimum of a continuous function is a classic problem from calculus. So, now we just need to take the derivative of the Hamiltonian with respect to q and set it equal to 0. However, we only need to differentiate the portion of the Hamiltonian that depends on m. We'll call this simplified expression h tilde. Taking the derivative of this expression with respect to q gives us this rather complicated equation. We still need the derivative of Fallhaber's formula itself, which is known and has this form. Substituting it into our expression leads to an even more complicated result. At first glance, it feels like we're heading in the wrong direction, only adding to the complexity. But this is where the magic of large N physics comes in. For very large N, Fallhaber's formula is dominated by its highest power term, and all other components become negligible. F of d of n is approximately just n to the d plus 1 over d plus 1. Substituting this leading order approximation into the derivative and discarding the lower order terms since they vanish as n approaches infinity, the n's miraculously cancel out, and the entire complex expression collapses down. What remains is this: a single, elegant, and weirdly simple equation that links the grounded set ratio q to the parameter d that defines the entire system. All the complexity of the sums, the matrices, and the configurations has been distilled into this one beautiful relationship. This is the master equation of grounded state. But as elegant as it appeared, his entire master equation was built on a foundation, a powerful but unproven assumption. His postulate was that the grounded state of the system is always two clean clusters. A block of plus ones followed by a block of minus ones. Simple, predictable. But what if he was wrong? What if the universe wasn't quite so elegant as he thought? What if the true grounded state, the actual configuration of lowest energy, was just a little more complex? What if the true grounded state was a chaotic, fractured landscape of countless small domains, constantly shifting and competing? If even one of these complex configurations had lower energy than his simple two-cluster state, his entire theory would fall apart. This was the central lingering doubt. To prove that the two-cluster state was the true grounded state, he had to find a way to analyze all possible states, including the chaotic multi-clustered ones, simultaneously. His strategy was to push the problem to its most extreme and abstract limit. What happens as n, the number of spins, approaches infinity. As n grows larger and larger, our discrete vector of individual spins begins to blur into something smoother, less like a sequence of points and more like a dense continuous line, as you can see here. This gives rise to a new mathematical object, a continuous function which we can call s of x and q. Here x represents the continuous position along the system, ranging from 0 to 1, and the vector q now defines the precise locations of the domain boundaries between the spin up and spin down regions. The beauty of this function is its generality. It can perfectly describe our simple two-cluster state, but it can yet effortlessly describe a state with 3 clusters, or 11, or any number of clusters we can imagine. Mathematically, this general function can be written as a product of sign functions, where lambda represents the number of domain balls, always one less than the number of clusters. With this new continuous way of describing any possible spin configuration, he could now do something profound. He could transform the entire Hamiltonian. The discrete sum over all spins I and j becomes a double integral over all positions x and y. The discrete tension jij becomes a continuous function, x to the power of d plus y to the power of d. And the discrete spins Si and Sj become their continuous counterparts, S of x and q and S of y and q. He had taken a discrete combinatorial problem, which was brutally complex in its original form, and recast it into the language of continuous calculus, a world with powerful tools for finding minima. The next step was to actually solve this integral, a significant mathematical challenge in its own right. The result is this analytical formula for the energy H, which now depends on D and the set of all domain walls Q. Now, he could finally answer the lingering doubt. Which configuration truly has the lowest energy? The simple case with just one domain wall where lambda equals 1, or a more complex case where lambda is greater than or equals 2. Let's look at the simple case first, 2 clusters where lambda equals 1. The formula simplifies beautifully, and upon optimizing the boundary positions Q1, the resulting energy H1 is always negative. A negative energy signals a favorable low energy state, reinforcing the physical intuition that this configuration is naturally perfect. But what happens when we introduce more complicated states, where lambda is 2 or more, and we have more domain walls? Here, the analysis gets a bit more subtle, but the conclusion is even more striking. To find the minimum, he took the derivative of the energy with respect to one of the domain boundaries. The critical condition emerged. The derivative must be a product of 2 terms, and that product must equal 0. The first term, which is governed by the ordered sequence of domain walls, one after another, could never equal 0. And that leaves us with only one possibility. For the system to be at minimum, the second term must be always 0. And here lays the crucial insight. If you look back at our original formula for the energy, that second term wasn't just a component, but a key factor in the whole expression. So, if that term is forced to be 0 at any minimum, at any critical point, we have the entire Hamiltonian H lambda collapsing to 0. But what about the boundaries? While considering the boundary cases, it showed that if any domains were to merge, the system would simply decay into a state with fewer domains, shedding interfaces until it eventually reached the lambda equal 1 case, the single domain wall configuration. To understand this better, let's consider the following example. In the plot, we observe 4 clusters, 2 with spin plus 1 and 2 with spin minus 1. Now let's consider what happens when we gradually shift the boundary of the third cluster step by step to the right. As the boundary moves, the third cluster starts encroaching on the fourth. Eventually, the spins from the fourth cluster begin to add up to the third one. After a while, the fourth cluster completely merges into the third and fades away. At that point, we effectively have one domain wall less. But what happens if we apply this same process to every domain wall in the system? In the continuous limit, every lambda tends to lambda minus 1. This reduction continues until, in the end, we are left with only two clusters, as expected, one fully up and one fully down. This merging behavior reflects how the Hamiltonian evolves, and so the proof was complete. The two-cluster state with its guaranteed negative energy is the only stable, energetically favorable ground state. Any other configuration with more clusters is either fundamentally unstable or is forced into a higher energy state of 0. The assumption was no longer an assumption. Order wasn't just possible, it was inevitable. The proof revealed a world both stranger and more elegant than anyone had imagined. So, the two-cluster state is a mathematical certainty for this system, a clean, predictable pattern emerging from a sea of chaos. But what does this actually mean? What kind of world does this simple rule, j of ij proportional to I to the power of d plus j to the power of d, describe? Let's return to the rule that started all of this. The tension, the interaction strength, is based on rank. Imagine a society or any system where its members can be ordered along a single axis by wealth, influence, or social status. The index I is simply their rank on this list. This creates a deeply counterintuitive situation. The tension J is actually lowest between the elites. A disagreement between rank 1 and rank 2 creates very little conflict for the system. Their relationship is low stakes. You could say they are friendly in the sense that the system's physics makes it easy for them to cooperate. But this apparent friendliness has little to do with emotion. For the powerful, cooperation isn't about friendship. It's just good business. And it's a business that follows the oldest rule of the book. Power protects power. But for the people at the bottom, the situation is the opposite. The tension J is highest between them. Their relationship are high stakes and competitive. This creates an immense local pressure for them to disagree. And the system is riddled with rivalries, where every individual link wants to resolve into opposition. So, here's the central puzzle. The most powerful forces in the system are pushing the poor towards internal chaos and conflict. And yet, we know from the proof that they ultimately align into a single, unified block. How is this possible? Well, the proof reveals the system's stunning solution. It is a global optimizer, and it finds a loophole. It realizes that the energy payoff from creating one grand disagreement between the rich and the poor is so enormous that it's worth paying a steep price to achieve it. That price is forcing the poor to do the one thing they are pressured not to do. They are forced to agree with each other. This is the Great Schism. The unity of the poor is not born of cooperation. It is a forced peace, a strategic arrangement imposed on them by the system's cold, global logic. And the unity of the elites is simply the low-cost foundation for this grand structure. Where does this strange and beautiful theory come from? Is it just a mathematical fable, a thought experiment I've constructed for this video? The answer is no. What we've just uncovered together isn't just a story. It's this. A paper published just recently in the prestigious journal Physical Review E that lays out the entire proof and the principle of the Great Schism. So, who was this student who dared to solve an impossible problem with a single, imaginative leap of faith? The reason I know his story so well, the excitement of discovery, the nagging weight of doubt, and the final relief of the proof, is because that student was me. I began this journey in the final year of my physics degree, a curiosity that grew into a full-blown obsession. I was fortunate to be joined on this path by my brilliant collaborators, Mahmoud, Alireza, and Dr. Halatai, who helped turn that initial spark into a rigorous mathematical theory. In the end, that's what this story is really about. It's a testament to the idea that sometimes the hardest problems aren't a wall, they're an invitation. An invitation to take a leap of faith.